In this video, I will show you how two computers anywhere around the world can communicate with end-to-end encryption using the Diffie-Hellman algorithm. I will also show you a practical demonstration by having a communication between two microcontrollers, and it is based on very simple mathematics, as we'll see. So let's see. So before we get into Diffie-Hellman, we need to start with some modular arithmetic. So this sign over here means B divides A, and we want that when we divide uh, A by B, we want it to give a remainder. So for that, A should be equal to some constant times B plus R, and R should be uh, greater than 0 because we want a remainder, as I said. Next, and R should also be less than B, because what's the point of remainder if it can be further divided? One more B can be extracted out of it, right? You get my point. So next we have this A mod B. This mod is short for modulo, and it is essentially equal to the remainder of A divided by B, so which was R. So yeah, next, um, if A is congruent to B mod C, if A mod C is equal to B, sorry, if A mod C is equal to B mod C, so now let's see some example. So here I have the numbers from 1 to 9, and what I've done is I've taken the mod 4 with each of these. So 1 mod 4 is 1, 2 mod 4 is 2. So you can see 1 mod 4 is 1, 2 mod 4 is 2, 3 mod 4 is 3, and 4 mod 4 is 0. Next, again 5 mod 4 is 1, 6 mod 4 is 2, 7 mod 4 is 3, and 8 mod 4 is 0, and 9 mod 4 is 1. So this is so all when in modular arithmetic, all if we're dividing by n, then the output of this expression, any number mod n, can have a max value of n minus 1. In this case we were dividing by 4, so the max value was 3. So now, oh right, so you can see it follows a pattern. It just rotates around these values. The values just rotate around these values. So if I want to find 1 mod 4, all I need to do is to start at 0 and just move one step like this from 0 to 1, and we have 1 mod 4. So this was 1 mod 4. Next, if I want to find out 2 mod 4, I just have to move 2 steps from 0. 1 step, 2 step. Similarly, if I want to find 6 mod 4, I just have to move 6 steps from 0. So let's do that with white. So from 0, 1 step is 1, second step is 2, third step is 3, fourth step is 0, and we are going to loop back up. The fifth step again takes us to 1. The sixth step takes us to 2. So in sixth step we reach 2. So 6 mod 4 is 2. Right? You get my point. Okay, so next we'll see the Diffie Hellman algorithm in action. I mean the key exchange mechanism, where we will share this. We will have a shared secret, a common key between the client and the server, so they can use it to decrypt and encrypt all the communications. Okay, thank you so much. So now I'm going to talk about the Diffie Hellman algorithm to generate a shared secret. So so we have these numbers G and N, which are public. They are known by everyone, and a random number, and we have two parties, Alice and Bob, who want to communicate with end-to-end encryption privately. So for that to happen, maybe Alice has a key which is 6, which she wants to send to Bob. So Alice wants to send the key to Bob, and they will use this key to encrypt and decrypt the traffic. So basically, maybe Alice will shift all the letters in the message by 6, and then Bob will just reverse that. But if she does this, if there is an eavesdropper listening to their communication somewhere over here, she will see that, hey, Alice is sending Bob 6, so she will also use this key 6 to encrypt and decrypt and basically cause a problem. So how do we do an end-to-end encrypted communication? So first of all, there are some numbers that that everybody publicly agrees on. Those are G and N. The number G can be small, but the N has to be relatively big. I have chosen 23 for ease of computation, but it's not, and it's the example from Wikipedia. And so what I'm going to do is, these numbers are public. Everybody knows Alice, Bob, some Eve, some, I don't know, whoever. Everybody knows them. Alice chooses a random number A, and Bob chooses a random number B. What Bob does is he takes G raised to the power B mod N. And this is why I was saying G can be a little small, because something like if G was, let's say, 2, and if B was 90, so 2 is to 90 is a really big number. I cannot even count the digits. Let me check what it is. So 2 to the power of 90, it is in the order of 10 raised to the 27. So this is why I said G can be relatively small if B is really big, right? So even if we take this, in this example we had 5 to the 15, so 5 to the 15, wait a second, what is 5 to the 15? Let me use my calculator. Is 30517578125. So that's why I said that you don't need a very big value for G. Next, what we add is N. So earlier I told you about this circle. So if I chose 4, there will be four possibilities for G to the B mod N and G to the A mod N. So it will make the work easier, but N is humongously large, and it is really difficult to decode if how to solve this. I think it is in thousands of bits, the N size. and you have to see how many rotations did happen in this if you are trying to guess. So it's really difficult to guess, right? So back to the point. Next we have g to the a mod mod n. Alice calculates this value, Bob calculates this value. Now through the public channel, Alice sends this value to Bob and Bob sends this value to Alice. And so what will be this value? So g to the a mod n will be essentially equal to 5 to the 6 mod 23. Let me just calculate it. So 5 to the 6 modulus 23. Just a second. So let's calculate this. Where is modulus? I need to use Python to get it. Wait a second. Python 3. So we have 5 asterisk 6, i.e. raising the power, mod 23. This resolves to 8. So 8 reaches here, and let me quickly get the other one. So I want this will be equal to 5 to the power 15 mod 23. So let's do it. 5 to the 15 mod 23, which is 19. So 19 comes here, and this was g to the b mod n, and this was g to the a mod n. And here comes the fun part. Now Bob will raise this to b and Alice will raise this to a. Remember, only Alice knew the value of a and only Bob knew the value of b. They randomly chose it. So, and then what they will do is they will do the mod n of it and mod n of it. So you will see what will happen. So g to the b to the a will be g to the ab mod n mod n, and this will be also the same. So g to the a b mod n mod n. So let me just show you that they have got the same value, but let's do the calculation for a second. So what we have is g to the b mod n was 19 to the power a, which is 6 mod n essentially. So mod n is 23. N is 23. Someone is using their phone near me. So next, print 19. Oh, and by the way, I'm using Python to do all these calculations. That's why I'm saying this word print. So don't think I'm crazy. So this turns out to be 2. Let's highlight it, and let's see this, what this turn out to be. 8 to the power 15 mod 23. Let's keep colors consistent, so I will keep it red, and this will be equal to, oh sorry, where it's coming, getting crazy, is equal to, sorry for the inconvenience, print and drum rolls please. This also turns out to be 2. So over this unsecure public channel where anybody could have eavesdropped through their communication, they have secretly shared they have generated a shared secret. So this 2 and this 2 here is a shared secret, and now they can use this to encrypt their messages, right? And you might think that what if you and someone was eavesdropping, they would have got j to the power 8 mod n and g to the power b mod n. If they multiply these, they will only get g to the power a plus b mod n, something like this. So they will not be able to get g to the power ab, and that's the beauty of it, right? They will not be able to get g to the power ab. They will get g to the power a plus b, which is a completely different thing. Okay, so I hope you get my point. Next we'll see the practical implementation of this using 2 microcontrollers. Sorry, I'm having some trouble with my code, so I'll show the practical demonstration in the next part, and I will release the next part within a week. Sorry for the inconvenience. I'm working with my microcontrollers. There is some, I guess, problem with the bootloader and stuff, and I don't know why there is some problem with the programmer getting out of sync, so I'm not able to program these through Arduino IDE. So just wait for a week. I'll make sure I fix this problem, and I will upload the second part in which I will show you the practical demonstration.